Huai-an, you can start.
Okay. Good evening, everyone. Today, I will be presenting this paper, The Federated Learning of User Verification Models Without Sharing Embeddings. So this is published in ICML 21. And here is the outline of my presentation for today. So as we know that user verification models have multiple forms of modalities across many kinds of applications. For example, we have face verification, we have voice verification, we have fingerprints verification, all of them. And a lot of them are being used on mobile devices nowadays for maybe for unlocking, maybe your cell phone, or just using some specific services only for the owner of the cell phone only. So as we know, that user verification has many multiple applications around. And all of those verification, they have this user verification models, which they are based on embedding based classifier. So what does that even mean? So here I'll give a quick explanation. So the embedding of data should be close to its user and away from other users. So you can see of those embeddings as like maybe some user characteristics or some user preferences across the view. So as we can see that this graph on the left side, the X is like the input of the data, and GX means like the output of your model, of the verification model, and W, which is weight, which is the W. It means that the vector that defines what kind of the user and the relation between the user and the output of the data. So here's a better explanation of this graph. So as you can see, we use the same W here as the embedding vector here. So we can see there are like 4 different users in this graph. So there's a user A, user B, user C, user D. And also there are some points around that. These are the model outputs of GX. So all those dots near them means that those embedding, those output results, they are related or close to the embedding vector of their own user. So as you can see in this picture, all those dots there that belongs to the user, they should be close to the user and at best far away from all other users. So this is the basic concepts of user verification models. They use the embedding. So from this simple example, we can see that in order to train this user verification models in a machine learning purpose, we need 2 things at a time. So the first one we have to ask is like, how do we train those user verification model, which is calculating the loss function. As for loss function, we can divide them into 2 types of concepts. First one is the positive loss function. So which here is the purpose of this one, positive loss, is to minimize the distance of GX, which we said, the user output, to the embedding vector of corresponding user, which makes sense, right? Because if you are if the user and he uses the data and the output should be close to its own preference or its own characteristics. And the second one is the negative loss, which is the opposite, which it focuses on maximizing the distance of other users. So it's basically the same concept as what we just mentioned from the last slide. It's basically saying we want to train this model to calculate the loss, and this loss, first of all, it should be close to its corresponding user and far away from other users to make the classification more accurate. So here we have a little bit of formula, which is L equals loss positive. So it's a positive loss and a negative loss. And this number it can be any kind of value, depending on what you define it. And here is a more detailed formula. So positive loss means that this is determines the distance between gx, which is the output of the data, and then this wy means the corresponding user embeddings. So wy here means the y means yourself. As for the negative loss, is the opposite, which is minimum of the distance, the distance of gx and wu. So this u means that it's not it's from other users besides you. So with this formula, we can see what we need to how to train a UV model. We need to calculate the loss function, and the two things we need for collection is, first, we need to know the data, and second, we need to have the information of the embeddings. So we have two needs for training the UV model, and in general, we need data for training and the embedding vector. So first of all, data collection. This is encounters the privacy issue, because usually when we train these user verification models, we need a massive amount of data, and in that case, if we try to collect data across many multiple users, those users will expose their data information. So the very straightforward solution to this was federated learning, because federated learning, they share only the weight data. The W here means like is the gradient, so it's not about the embedding vector in this case. So basically, yes, as we all know about federated learning, basically it can help the users to share their gradients without even need to sharing the raw data, which is the privacy concern. So data is not an issue. We already solved the issues for data. So the other challenging part is the embedding vectors, because embedding vectors cannot be shared with other users. And in general federated learning cases, a lot of the classifiers, they use public general classifiers. So like for image classification, we have car and cat and dogs, which are already public. But here, because we're using user verification, the embedding vector itself is an information from the user. So those embedding vectors cannot be shared with others. So hence, without if we cannot get the embedding vector, we cannot calculate the negative loss. So what happens if we ignore the negative loss when calculating the loss function? So if we do the training with only positive loss, what would happen? It will end up, we will collapse all the embeddings into one single point. What that means is that because there's only one variable in the formulation, the end is obviously going to be loss equals 0, and and all the results will just collapse. So right here, because embeddings cannot be shared, we cannot calculate the negative loss. So if we only use the training, it would get the issue what I just mentioned above. So we have to think of a way to deal with this negative loss calculation issue. So now this paper, they introduced the Fed user verification design. So what the contribution of this paper is, they use user verification without sharing the embedding vectors. How do they do that? We should mention that we need embedding vectors to calculate the negative loss. And the second claim, they claim that they have comparable performance with existing approaches, which means that even they use their method, it's not going to really slow down or lower the accuracy that much of the result. And also they talk about this is based on using error correcting codes as secret vectors, which we will be talking about it later and in the presentation. So about this very user verification model, we will first use a definition of the loss function. So let W, big W, be a set of C vectors. So C is a constant, and VU be the secret vector for user U. And what they try to do is try to make the negative loss be negligible, or in a case that you don't need to calculate the negative loss to get the general, to get the approximate loss function. So in this formula, you can see the original loss function is just what we mentioned back there. So the left side is the positive loss, and the right side is the negative loss. So as you can see, because this WU cannot be shared, so we cannot calculate it. And what the Fed UV they claim is that we change the definition of it to this one, which is changing from embeddings of a current user to a secret vector, and times by the secret vector for user Y. So here and this one, we can just say this is we call them a secret vector. So they change it from embeddings to a secret vector. So later on, I will be talking about how they changed all this thing. So first, we will talk about how they define, as they claim in this paper, how they define the positive and negative loss terms as follows. So as first one, positive loss is the maximum of 0 and 1 minus the right side of this. So as you can see, this one, this one on the right side, and it means the secret embedding of what we just mentioned lesson. And this V is the true secret embedding of user one. So this positive loss, to call it in a more mathematical way, is that the positive loss term maximizes the correlation of the instance embedding, which is the one we mentioned the right side, with the true secret embedding. And the negative loss is the opposite, which is the maximize the correlation with secret embeddings and the embedding of other users. So this is still the same concept as we talked about before, right? Because loss positive, it should be seeing the the correlation between your output and also the user, the user itself. And the negative one is the output of the data with other users. So, okay, so now we have established that this is their definition of the positive and negative loss. Now we will look at lemma 1. So here we assume that the absolute of this secret embedding is equal to root C, and the Vy is equal to vector of either 1 or -1 with the dimension of C. So for the definition for the loss positive defined in 4, which is the definition right here, we will have the loss positive equals to 0 if and only if this secret embedding equals to Vy, which is the true secret embedding itself. So here's a bit of proof. So if we say that we say Z is equal to secret embedding, so this is our this is just a change of way of saying this. So the term L plus equals to 0 is equivalent to C is equal to this bigger than 1. It should be obvious by this term. So for the max, so for loss, for positive loss to be 0, that means 0 must be bigger than the right side. So that means 1 minus what is mentioned in the right side, it should be lesser than 1, right? So if you do that, if you try to do that mathematically, you can see that okay, so this has to be larger than 1. And now, so we can say that this equals to this Vy and Z, which is the secret embedding, equals to 1. And the equality holds if and only if Z equals alpha Vy for alpha at larger than 0. And since that Z and Vy are equal to C, why we can tell this, because this is our assumption right here, right? We assume that this secret embedding is equal to C root. And Vy, because it is based on our assumption, so the size of this is also equal to root C. So alpha equals to 1. So in that case, we can say that we can say that alpha equals to 1. So in that case, we can say that in order to have L positive to be 0, we can only say that the secret embedding is equal to Vy. Keep in mind that this Vy is the secret vector of user Y, which is itself. So this is the first lemma for the proof. And then, so now we establish this first concept. We'll now sort of jump out of the box and talk about error correcting codes, which is ECCs. So ECC error correcting code is basically a technique that enables restoring sequences from noise. And it is designed to maximize the minimum Hamming distance between distinct code words. So this might be a little bit far off from what we were talking previously, but as you can see, the concept here is maximize the minimum Hamming distance, which we will find some relation between this and our work. So this is another theory, which is the last one, by the way. So again, we assume that the secret vector, the secret embedding is equal to C root, and Vy, the secret vector, is formed this way. If we assume that those users, those secret vectors of user U are chosen from the ECC code word. So in that case, that means that those vectors we just talked about, they assume that they are used from the ECC code word we just mentioned from last page. So if we have those two assumptions for L pos and L negative defined, and for, as we just mentioned in the definition of positive loss and negative loss, minimizing out of all these concepts, minimizing L pos also minimizes L negative. So why is that the case? So here we will see a proof of the case. So we will say since VU, what we just mentioned, is based on this form, is the dimension of C with either -1 or 1. So the Hamming distance between VU1, user 1, user 2 of the secret vectors is defined as follows. So as you can see, this is the Hamming distance. All right. So as Hamming distance, we can get this result on the bottom side. So what does this try to do? The ECC code words, it's supposed, as we just mentioned here, it's supposed to design to maximize the minimum Hamming distance. So in here, in order to maximize this Hamming distance, what we will establish is that this term must be minimized in order to do so. So these are the two theorem 1 and the lemma 1 we just talked about are the two fundamentals of why they define and they design it this way. So to wrap it up, what we just talked about, according to lemma 1, the negative loss should be the maximum of u. This means that the user y and user u are different. This is the definition. Should be the value for a negative loss. And according to theorem 1, the ECC, the error correcting code, they minimize the maximum of u, user 1 away from user 2, which is the one on the right. So you can see these two are very, very, very similar to each other. If we can see those two, the lemma 1 and theorem 1, we can say that negative loss is at its minimum when, first of all, positive loss has to be 0. This is what we established in lemma 1, right? And VU are chosen from the ECC code words, because the ECC code words they accomplish the same thing as our algorithm here requires, right? If we replace this user 1 to u, and we replace this user 2 to y, you can see that these two are basically the same. So if we use those code words, we use the code words from ECC, we can guarantee that we can get the negative loss at its minimum when positive loss equals to 0. So what does this accomplish? You can why do I need to talk about all those theorems and lemmas? Is because that, as you can see, in order to get this result and to get this conclusion, negative losses as minimum, we don't even need to calculate them. And of course, if you don't care about privacy issues, you can still do the old route of calculating negative loss. But if here we consider the privacy issue, we don't even need to share those embedding informations in order to calculate negative loss, because negative loss is, you can already know when is the negative loss is minimum. So what we established is that minimizing positive loss also minimizes negative loss. Hence, there is no need to calculate the negative loss. So now it's like, how do we construct the secret code words as we just talked about there? So the structure of secret code words is, first, it is concatenate with the list of numbers, binary numbers. So the first part of it is supposed to be the unique binary vector representing user ID. And the second part is the random binary vector chosen by the user. So here is a structure of the secret code words. So as you can see, this message right here, this whole message right here, we have the uniqueness because the first part of the user ID is always going to be unique, right? So there's no not going to be any repetitive cases of the messages because every user is unique. And then we have this secret random vector because it is chosen randomly, and it chosen randomly. It can be kept secrets because it would be harder for the outsiders to even guess what is the exact binary vector here. And also we have the parity bits for security issues. So in this paper, they use the user ID they set here is at least 22 bits. And also that stands for the same for the random vector. Also at least 32 bits. So with this combination, combination of those binary vectors together, we can get a new secret code word for every single user. And also those users, they have secretly protected code words. And those secret code words are called secret vectors in this paper.
I have a confusion here.
Okay.
Previous part I can understand, right? So you try to represent your own vectors with some coded approach, right? For example,
Yes.
you ECCS or whatever. But how can this kind of random pickup vector to reflect your own embedding features? So according to what you said, the ID definitely you can pick up, there is no problem. But for the random vector, the secret vector here, I thought it should be related to the embedding vectors, right? Embedding features. But here, according to what you mentioned, it's nothing related to the embedding vectors. It's just randomly chosen.
Okay, so what I mentioned about random binary vector, it means that this random vector, it is completely random, but the choice is by the user. So which means that the user can they can choose what the vector composition they want to be formed.
Yeah, exactly. But how that can represent the embedding features? Say if you try to convert this, you try to convert your data like this, or you try to convert your embedding vector into this random vector. I mean, what's the purpose for the message here?
Okay, so the purpose for the message, basically they just wanted to give this set of code word, the uniqueness and secret properties for this message. So that way.
So they do the final training with this message, or,
Yes.
or this kind of message like the message head of the, I don't know, the gradient or something.
Yes, because they pretty much use this as for every user it's different, so they can pretty much train with it, right?
But what do you mean by train with a random vector? I mean, if it's not specifically chosen, the random vector does not mean anything, right? So say if you train with this, you use this to replace the gradient, or you use this message to replace what?
What they try to do, this secret vector is to replace the embeddings of the user.
Okay, then what's the relationship between the random vector with the embedding vector? There must be a relationship, right?
So yeah, the relationship is basically established on this user ID right here. because like every user, they have different ID. So if you do this, and if you get this for your embedding, you can guarantee that it is different from others. And this is basically because it's a random vector and the user ID. So this is like a combination of both of the properties. So it has its own, you can say its own characteristic or tendency because of the user, and also it adds the randomness to the vector as well.
Okay, you can continue. Let me say what's going on. But here, yeah, user ID can be unique. You, at the tail, you add some randomness, but it does not show any feature of user's data or anything. It just show the message from different users. That's it. Right. So I don't know how should this be connected to the file learning, but anyway, yeah, you continue. Let me see what they're going to do.
Okay. All right, so this is how their structure of the code words stuff. So pretty much their model structure of this federated UV is basically, so as the same, we have this X and into G, which is the same as what we just talked about. So GX is the data output, and W is also the same as we just mentioned before about the set of W that can that forms the secret embeddings. So because W times the secret vector is equal to the secret embeddings, and this scale here is basically just the concept of it's basically a concept of just keeping the input have the norm of root C. So here the loss function here.
So okay, when in this structure,
yeah,
where did you put your message? The message is X or what? The message in your previous slides is X as the input here?
okay. Oh no, so this, the X here is the data.
Yeah, I believe so. X is your training
yes,
data, right?
Yes.
You got a JX. Then where you put your vector, you put your message. I mean,
okay. Basically, this GX times W is already like one of the secret embeddings for one of the results for it. Because what we talk about here, this secret vector, this is equal to W times VY, right? Because VY is like the true secret embeddings of this, and the one here, what I just mentioned here, is X is the instance embedding. So it's like because each dot, you cannot be like completely the same as the embedding point of the user, right? So this is basically just close to the X, the data X should be close to GX should be close to the true secret embedding, what we just mentioned here. So
no. I just want to know the random vector here can be mapped to what? Can be mapped to X, JX, or the one after W box, or Z? Is equals to what? The random vector message.
okay, so the random vector message should be GX here.
Should be GX. GX is your local train, right?
Yeah, but oh, I mean, like in this structure, they didn't really they don't really show the secret vector, because this whole process It's processed by a data. This is it. This is like an instance data for it. It's not like the identification of a user embedding, right? What we get as this z as the z for our result is just like is supposed to be like close to what we talked about the secret embeddings back in the last one. So the secret embedding will not be shown like in this structure.
I don't know what you're talking about, but I just want to know where you put that message structure in previous slides during the federal learning process. Where you put that? And the first question is that. The second question, why that vector, the so-called secret vector, is randomly selected? Why? Where you put this message during the gradient updates procedure or what? That's a simple question, right? If you, I don't know if you clearly mention in the paper, but they give this structure, they should mention where they're going to use this message structure, right? Where?
Okay. So they use this message structure like
is it serve as a package head? For example, you do a networking transmit a packet, you encapsulate something, in the package head, right? You learn from the wireless networking class, right? Is it something like that? Or this random vector has certain meanings there? That's the things I want to know.
Okay. Yeah, I will go back to this slide here. So yeah, right here, as you can see that right here. So this is the secret vector there. This Vy and this Vu is the secret vector they just talked about.
That's true. But for that Vy and Vu, you have a certain kind of way to build it up, right?
Okay, so how to build up? So basically, this is like determined like use like server. So server will give each each user like a user ID, right? Like a unique user ID, and the users, they will choose like the random vector to concatenate with the unique ID. So this is how they generate the vector.
I don't think they randomly pick up that vector. You talk a lot of things, you use the Hamming code, this and that. You need to construct that secret vector instead of randomly pick up. You know what I mean? It's not randomly pick it up. Your secret vector is follow the way, follow your theorem one, whatever they prove there, follow the Hamming code construction, it's a structure over there. You carefully, deliberately construct that secret vector. It's not like randomly pick up by the user, right? So, but for that message structure you show me, you told me, okay, for that secret vector, you randomly pick it up. You don't follow any kind of procedure to construct it. That's my question coming from. Because that slide is totally, irrelevant with the rest of the slides. First of all, I want to know where you put that message, right? The second thing is the random vector, the secret vector, is something like you mentioned, randomly pick it up, or follow the procedure they mentioned here. You construct that by purpose. You got my question now, right?
Yes.
Yeah, you answered the question. You were the guys who read the paper, answer the question.
Okay.
Hey, Huai-an.
Hey.
So if I understand it correctly, I think you see the original loss function you mentioned there's a distance this is a distance measurement between the GX, which is from your deep learning model, the model generated embedding vector, and the WY is the true embedding vector.
Yes.
Comparing the original loss function with their proposed method, they just used the big W transform VY to replace the true user embedding vector. I see the VY here in their paper is the random vector you mentioned. So what they are trying to do, maybe they are using a linear projection of the user randomly chosen vector to serve as their true embedding vector. But this W is learned federatively. So, I mean, the W here is learnable. So even the user, if you're the user, you only use the random vector VY, VY to share with your peers. When you run federative learning, the model or the system will learn a W here. So the W here, the big W, this projection will serve as the true jointly with the random vector VY will serve as the true user embedding vector. So I think
the VY here just like an initial vector.
Yeah, I think they just 0 and 1. They are binary vectors. They do not contain any information from users' data.
From the fed learning, you try to train the projection function WT here, right? So obviously the W here.
Yeah, I think the W here is learnable, right, Huai-an?
Yes, that's right.
So I think they are trying to learn this projection function, and this projection matrix, and this matrix can have can gather the unique information from all the users, but nobody really knows that. So that can be safe and secure.
So the W is only going to be known by individual user, or the W is like a global information. The W will be published at the end, right? But nobody is going to know what exactly the original random factor.
Yeah, there's no embedding vector sharing among users, but they all jointly learn this W.
Okay. W is public, and VY can be chosen. Okay.
And you do not know others random selected vector VY, so you do not know others vector embeddings.
Okay, that's the magic here, right?
I think so. So that's it correct? I don't know.
Yes.
Wow, you need to learn the way to answer my question, right? To say, Chen Pei can answer the question. He didn't even read the paper. He probably just read the paper within the last 5 minutes to 10 minutes. Don't scare off me. You do the discussion with me all the time, right?
Yes.
I just want to know the answer.
Okay.
Also, I think at the beginning, you need to find a way to show people, to show the audience what Chen Pei mentioned just now, right? For example, you start learning, okay, you do this, you convert that to this. Okay, you need to make people know what kind of information is private, is probably kept by individual user. What is public information, trained by fine learning? That's the ultimate goal. We want to know the W, something like that, right? And also you show them, before we go to the proof or say how WT times VY can be equals to small WY, you need to show all the procedure, let people know, okay, that's the thing we're going to do, right? Then you go to the detail. The procedure can be like, short description, or it can be just like a figure, like pictures, animations, whatever, right?
Yes.
Yeah, I think if that's the case, I think it's very interesting. Make all the proof afterwards, you know, make much sense.
Okay. Okay.
Yeah. But I didn't quite get the magic still in details, but in general, if that's the thing, yeah, it's kind of interesting. But the thing is,
Yeah.
okay, you can randomly choose VY. You join to learn W.
Yes, that's basically the concept of this fed UV.
So every time you have the same VY, right? Not the same way. Okay, it's the same. Yeah, the same VY. Okay, so the random actor you choose. Okay.
Yeah, because the VY is different for every user. So every user, they can like get the maximum of the correlation between their instance embedding with their true secret, with their true embeddings of those. So every time they will be getting a unique different value or
Okay.
result.
So,
Yeah.
so later, how can you replace VU with the GX? Could you show me that slide? So now, you know, we cannot share VY and VU, right? So yeah.
Yeah. So basically, this functions like VY is yourself, so you can.
Yeah.
You can
VY
use-
is known by yourself.
Yeah,
Okay.
and VU is the one. Yeah.
How can you replace VU with I don't know, the J theta or something?
Okay. You don't actually replace any of those. So basically, if you want to calculate the negative loss, you have to get this VU. But what they try to do, and as like the process of improving, they basically they made it so you don't need to exactly calculate this. You only need to get the minimum value of positive loss, and the outcome is gonna be. It also means that you will get the minimum of negatives. That's basically the concept of it. So you don't really need to get you don't really need to get the information of this VU. You just
How do they achieve that in general? They use the Hamming distance coding
yes
to do that?
yeah. So like this is like the first one I just started this lemma thing. So basically this one is just showing that okay, if we want to have positive loss, we have to be like this Z, which is this this WG X equals to VY. So this is first lemma. And the second,
sorry. What's the WG theta X here? It's like still the projection you want to train, right?
This is like the secret embed. This is a secret embedding of user of data X here. Yeah.
Of data X. Secret is embedding. Okay. So given a training data set, okay. Okay, could you go to the next one?
Okay. Okay, not this one. Yeah, this one. Yeah. So yeah, what this theorem tries to say is that because the Hamming distance of this is defined. This is like the Hamming distance, right? The outcome is this. So what the ECC code tries to do is they maximize the outcome, right? So if they want to maximize this result, they have to minimize this term right here because it's minus, right? So what they try to do is minimize this term right here.
Yeah. So here, minimize the positive loss also means minimize the negative loss. But if you use Hamming,
yes,
if you use the ECC code, right?
Yeah. Yeah. The magic here is because the ECC code they have this property of getting this maximized value. So that's why if we use the ECC code, we can guarantee that minimizing positive loss will get negative loss.
So in this way, you don't need to calculate the negative loss, right?
Yes, you only need to get the
positive loss. You only calculate the positive loss. Is supposed to calculate. Okay.
Yes.
Okay. Okay. So you only need to learn the projection. As long as you learn the projection, everything is solved, right?
Yes.
Oh, okay. Okay.
So yeah, so that is basically what the the loss function here represents. Because so right now, because we don't need a negative loss, we can
Yeah. Could you go to the first one?
okay.
I still try to figure out just the message here. Okay, it's like but I think the message here is nothing. You're not going to transmit some. Are you going to transmit this message?
No. This is just like this is like predetermined by the server. So the server gives you the user and user ID, and the user ID just chooses this itself. So this is like trained by yourself.
Yeah, it's trained by yourself, right? You don't need
Yeah.
to submit this.
Yeah.
What you submit is like the fair learning. You still submit the gradient, right? Then why? Then I got confused. Why they want to show the message format here, and what did the parity bits means here?
Okay, yeah. So parity bits is just basically tries to it's just for like security security issues, right? Because you want to make sure like the message
No, I mean, if you want to transmit the message, right? You give some parity bits, and this parity, whatever bits at the tail, in the end, it has certain kind of security property. As long as you want to transmit this message, if the message is kept by yourself, why you want to add the parity bits over there? I mean, this message is transmitted from who to whom.
Okay.
That's confusing part of. I mean, according to your and the Chin-Pei's explanation.
Yeah.
We don't need to transmit this message. Okay, as the user ID, I know my ID. I pick up my random vector. I do the training. That's it. I wait for the global, global updates of the W. Then I further train for the next round. That's the thing, right? So where is the message used?
Okay, so what this paper said here is like this parity bits is basically like it's just to like it's basically to guarantee like this is the vectors like this whole vector is like maximally separated. It's basically this parity bit just guarantees like this whole message vector. It can be maximally separated because of the use of the ECCE, the error correcting code algorithm here.
No, my question is, the message is from whom to whom?
It should be kept by the user itself.
Why then?
It doesn't seem to be like need to be transferred to.
Anyway, yeah, I don't want to waste everybody's time. You double check the paper to check the message for what? It's only to show us, what kind of everybody's message look like, or something. Because if it's only for yourself, I'm confused by the parity bits. Okay, and also it should not be called message. It can be called an initial vector picked up or something, right? But if it's a message, we're going to send it to somebody. I need to know from whom to whom.
Okay.
Okay. For the rest part, by now I can understand, but yeah, but I think you should be crystal clear about all these things instead of you need someone's help to explain that.
Okay.
As long as you post the slides here, you're supposed to answer the question related to this slide, right? Otherwise, you just remove this slide. If you think it's not related, I don't know why you want to post it here, right? So, yeah. But anyway, yeah. Continue, please.
Okay. All right, so that is basically so as the result for this value v, we can say that this we only need to calculate the positive loss function right here, which is as shown in here. And the sigma here is basically like a scaling function, which is just for the inputs of the system, they have the norm of root c. So that's basically it. So for the verification, so it becomes very simple, right? Because we only need to know if like this loss function is high enough or small enough. So here is just if this term right here is over a threshold of tau, it means that okay, the device like acknowledge you as the user, so they accept it, or otherwise they would just reject it. So as we can see, like from this method, we can tell we only need the positive loss after all. So with that said, we don't need to share the embeddings for that. So that's basically the concept of this paper, and like showing that why they don't need to share their embeddings. And here's like the implementation part of it. So in this data, they have many different data sets. So Vox Celeb is like a text independent speaker identification. They have Celeb A, which has over 20,000 facial images for training. And they have Minus user verification, which is like the handwriting identification for those data sets. As for the setting, they have 1,000 users, and they choose the BCH coding for generating the code word. And the baseline they want to compare is the first one is the softmax, which is the original federated learning with both the positive and negative loss function considered. And here, this one is FedOS, which is away from with spread. So this one is basically showing, this one is basically they can do they only need to share the embeddings with the server but not the users. So this is like a slightly better version of privacy in terms of privacy, but not as well as this paper claim, as this like full privacy from all users and also from servers.
So I need some further refining here. So for this data set is labeled, right? So they pick up like 1,000 users from each data set. Then they change the data. They use the BCH coding to change the data, right? To generate the code word.
Yes.
So they do some post-processing of those data, right?
Yes.
Okay. Then.
Yeah. All right. So that is basically the implementation, the data set, setting the baseline of it. So here's like their results for verification. So first is the verification performance. So these are the 3 different data sets for the use. So as you can see for this picture, so the y-axis is the true positive rate, and the false, and the x-axis is the false positive rate. So the better performance should be like the lesser the false positive rate of this should be, right? So as you can see here, softmax has the overall the best performance for verification because it fully calculates the positive and negative solutions. And here this is fed average width spread out here. So it's right here. So as you can see, these numbers represent like the code length of the model. So here, the green line, the red line, the purple line, they are somewhat they might have a little bit worse performance when the true positive rate is like equals to 1.0, but they have a pretty similar results, at least like close to 0.9, and that suits for all other kinds of data sets. And also there are times that the Fed UV is better than the Fed OS average with spread out. So from these three performance results, they're not trying to say that, okay, Fed UV outperforms all those previous ones. They're trying to say that those the Fed UV is on par with all those existing approaches for user verification here. So that's basically the verification performance. They're just trying to say that even though they lost a slightly bit of performance, they still what they got for trade-off is like the full privacy matters.
So
And
for Fed average, you still needed the embeddings from other users.
For so all of these they basically use the concept of Fed average, like all of them they use it. It's just it's just like if you use the AWS average with spread out, they only use users. They only need to share the embeddings with users. And for our work, for this paper claims, they don't need to share any at all. Yeah, that's basically the difference between these three.
Okay, gotcha.
Okay. And that is the verification performance. Now we will talk about like the performance with or without the negative loss. So here's the clear chart of showing. So as we can see, so the blue line is train, and the blue and the yellow line is with the negative loss here. So as you can see at the start, it's clearly that the accuracy of those training of those with a negative loss is going to be better. But as time goes on, it's going to reach a stable solution. So like over like pretty much like over 10,000, you can see that there is like slightly almost no difference between those two, because like for instance, if we take a look at the training data set, you can see like the green and the blue line, they are pretty much the same, even with or without the negative loss calculation. And as for the red and yellow line, that makes the same result, right? So as we can see from this, as a result, they claim that you don't really need to calculate a negative loss after all, with their method, of course. So this is the results for this paper for you. Now I will be talking about the conclusion. So Fed UV is a framework for training user verification models in FL setup. This is nothing new, right? Because what we talked about on Fed average with spread out AWS, they also use the same. But what they do here is they perform the training without sharing the embeddings, which guarantees total privacy. Also, their performance, they are on par with the existing approaches, as we just talked about with the baselines, the softmax and the Fed AWS. And they show the results from a variety of modalities. So that means like any kind of field of user verification, they achieve similar results, and that is a promising results for them. And that is pretty much it. Any questions?
Dr. Joe has a question in the chat box.
Okay.
Refer to part including the unique IDs.
Okay. Okay. The author borrowed the concept and used the term. Okay, yes, okay.
Okay, so
Yes. Mm.
what Dr. Joe means, but still, if that's the case, we still need to transmit that, right? So you don't need to
At least for my, yeah, at least for when I read this paper, I don't see they really need to transfer. All they do is like server give them the ID and they secretly choose and they just run with it all the time. Because only the big W is jointly trained.
yeah,
So
the borrow the concept to use the term of the message.
yeah, so I think yeah, what Dr. Zhou means is like basically because we use the concept from the ECC error correcting codes, and the error correcting codes, they have this concept message. So we just, and the message is just what it should be when we're using the ECC.
So you just abuse the message and they don't use it at all. That's what
Yeah, maybe they're just trying to create a they just try to create a binary vector in that case for the embeddings.
but for the embeddings, your random vector is good enough, right? So you don't need to, I mean, the mapping function should not be correlated to the user ID or something, right? Because it's not necessary. Although definitely it's possible if you put user ID there, you can still get a train.
Yeah, you yeah. It might not be necessary, but at least that in that way they can make sure that all the users they have unique.
So
Yeah, the unique ID is just for not
yeah.
people to get the same. Yeah.
So user ID is partial of the embedding vectors as well.
Yes, so like the whole the whole concept of the secret vector is what we just mentioned is it's been concatenated by user ID, the random vector and the parity bits.
Okay,
Yes.
so for the initialization, you can put your user ID there.
Yeah.
Put your random vector you picked up there. And like
yeah.
Dr. Joe mentioned, because they use the concept of coding code words. So they abuse the message concept. You put some parity bits over there, right? So when we train the W function, the WT function, the mapping function, you consider all of these things, right?
Yes, that's why I understand.
Okay. User ID. Okay, the parity bits have a certain correlation with the. Okay. But that one only make your training more. I don't know, more difficult, probably.
They did mention like a little part of like computational cost here. What they claim is that it's not really that big of a deal, basically.
But you still do the training based on your own data. Okay.
Yeah.
Interesting paper. So for the limitation, instead of I mean, besides using the ECC coding, is there any other limitation? But definitely you need to convert your things, for example, the data stuff into the code, right? Is there any other limitation?
I don't see much. Like they say that you can minimize negative loss by minimizing negative loss by two key assumptions, right? So it's like positive loss equals 0 and VU is chosen from ECC codes, but also like from the theorem and the lemma what I just mentioned here, they also like they do like have this assumption like, okay, this secret embeddings is the size of root C something. So if you're talking about limitation, I think that's basically what they show in here. They have some assumptions for those.
Could you go to the previous page?
Previous?
Yeah, one more. Yeah. No, not that. I think there's a claim one or lemma one, right?
Oh,
yeah. I wanna see the
right here. Yeah.
no. This is a. I want to see the lemma 1 page.
Okay.
Yeah.
Okay. Here.
Okay. Yeah. For
Yep.
our define
Yeah, because we have to like get this. We have if only if this is like they're one of the concepts.
Okay. Yeah, it's interesting. Yeah, basically there's not much limitation. Okay. Yeah. Any other questions, guys?